Welcome to my video. I am Arvind. Today, in this experiment, we will be seeing how to compute pulse rate of a PPG signal and the pitch period of the voice signal in Arduino using the pre-recorded data. Here, I have stored the data of around 200 samples in data and sampled at 100 Hz and for the frame duration of 20 seconds. And we'll be calculating the PPG signal not for a complete window of 2000 samples but only for 1000 samples, which is around 10 seconds. Usually we'll do for 5 seconds, but here as we have like more space in audio video, we are doing for 10 seconds. And we have 3 more arrays x, y and z. Here, actually, this experiment can be extended for real-time data, which can be stored directly in x variable. But as we are doing it for stored value, we are initializing one more variable so that this can be easily adopted for or accepted in real-time data. And then we have other arrays, peak value, peak index, which stores the peak value and the peak index that will be finding using this particular piece of. So here the setup. So as we are not taking the complete 2000 samples, we'll be doing it as a samples of 2 windows of each 1000 samples. We are having a count 0 which goes from 0 to 1, which is like window 0, window 1. So for every window 0 or window 1, we will be collecting 1000 samples. So as this is a marker is just from 0 to 1000, then 1000 to 2000. So that's what marker is doing. So marker takes a value of 0 in the when count is 0 and takes a value of 1000 when the count is 1. So in the first time, a collector goes from 0 to 1000 and x stores the value of data of 0 to 1000. The next window, x stores the value of 1000 to 2000. And then we are calling two different functions. One is like auto correlation function, method function, and other is normal function where we just find the peaks of the value of the signal and we'll be computing. Once we know the peak of the two peak difference between the signal, we can easily find the time period of the signal. So the same thing we are going to do. And as in the previous video, I showed how the normal method of finding peaks for the PPG signal to find the beats per minute. In this experiment, we'll be finding how we have to do using correlation method, and we'll be comparing the outputs of these two methods. So let's first see how the correlation method works. So correlation method, it is basically a product of delayed version of the same signal. So every correlation has a correlation coefficient. It is at time t equal to 0, what is the correlation between two signals? It is when there is no delay between two signals, what is the coefficient that I am expecting? And for R of 1 means when there is a shift of 1 unit, what is the correlation? When there is a shift of 2 unit, what is the correlation is coefficient of R of 2 in autocorrelation function. This particular piece of code takes the value of what is the uh, R of 0. So 0th coefficient is stored in R, and as we are normalizing the values, I am storing y of 0 as 1. As we know, uh, 0 when there is no time delay, the autocorrelation function will give maximum value as it is a product of two signals, same signal. So like without any delays means like it will give the maximum value for the fixed window size. So this particular piece of code finds the coefficient of R of 1, R of 2, R of 3 up to R of 1000 as length is 1000 and this whole function varies from 1 to 1000 and we have already computed y of 0 and we will here this particular piece of code computes the coefficient from R of 0 to R of 1000 and we are normalizing with R of 0. So let's see how this function gives the plot. I have already uploaded the code and this output plot gives two values in the sense as I'm running two different functions. So for the first 500 sample, it gives the output of the correlation function, and the next 500 samples, it gives the output of the normal method, how we use to find the peaks. So I'll come to that method later. Um, if you want to know about that this particular method, you can watch my previous video. Let's see like how the plot looks like. Uh, Blue one represents the input signal, that one represents the autocorrelation function. As I have scaled to 300, it is starting at 300. So as you can see, autocorrelation function dies down, and this is a place where 500 sample works. After that, the normal method which you used to go by using differentiation and all those stuff. And then this is again the 1000 to 1 sample second window, and it's finding the autocorrelation function of this particular data, and it's processing. Again, it is doing the normal way of differentiation and moving away its filter to find the peaks. So this is as expected as this is as expected. Let's see how to proceed after finding the autocorrelation coefficient. Let me comment it out, and we also need. Let me comment this out and comment, and this one also. Like, this normal method uses the same code that I have explained in previous video, and the link will be there in the description. Okay, let's upload the code. By the time I'll be explaining what happens next. So here, what is happening is, as we have seen, autocorrelation function is maximum for after every time period, but it crosses zero. I mean, autocorrelation coefficient can be negative sometimes when the correlation between two signals are not the same. So we are using that as our advantage, and we are finding. So here at every zero crossing and the value of y is greater than 0, I'll be finding what is the maximum value in that particular region between two zero crossing. So with that, I can find the maximum value. So as explained in the previous video, we'll be following the similar type of code where we'll be finding the maximum by considering all other, once we find the maximum, we'll make all other input except the maximum input, in the sense autocorrelation functions value, except the maxima to 0. So this is exactly what we are doing here, and we are repeating the same thing as we do in normal method. So let's see like how the program runs. Let's plot it out. The first 500 samples should be our autocorrelation function. As we can see, there is a delayed version. It's okay because we are using autocorrelation function. You can see for every peak there is an autocorrelation function's peak, and this is for normal method where we are finding the peak directly from the input signal. And this is going for the second window. Second window's autocorrelation function is giving the maximum value, and second window's normal function is giving uh, a maximum value. So let's see like which method, how these values are, how different these values are by printing and seeing, by calculating BPM. So we'll comment it out next. It's the same formula for BPM. Let's see, commenting it out. And for the normal method also, we'll see like what is the output of these two methods and how different these two outputs are. I will again upload it. Um, Here I have printed only for 500 samples. You can print for all 1000 samples, but then it's just for the sake of getting a feel of how these signals look like. I just gave for 500 samples. Um, let's wait till it uploads. It's uploading for every 173 pages. So it's done uploaded. So let's open this. So in the first window, the correlation method gives a sample of 85. It means after 85th peak, after 85th sample, we are finding one peak. That's what correlation method says. And with that thing, it is estimating the BPM to be 70. And in the normal method, where we find the maximum using the differentiation value, we are having after every 87th peak. Uh, we are getting a correlation, we are getting a maximum. So with this thing we are getting around 68 bpm. This is for the second window. So we can see like these two data are close to each other, and for this particular experiment they work normally. So this is the estimated bpm of the signal, and it's around like 68 70 around that range. This is a common thing, as ppg signal lies between 60 to 100. So our both the methods work correct. We can justify from this particular output. And now we'll see how this thing works for audio. um, Here audio, this is exactly the same code, but sampled at 8000 hertz. 8000 hertz means like in 1 second we are getting 8000 samples. So here I have downsampled it to 500 milliseconds. So this data has 400 samples, and I am considering the window length to be 240 samples, that is 30 milliseconds. So once after every 30 millisecond I will be processing the data. So here also the same xyz variables, and there is no difference between previous values, I mean previous code and this particular code. um, I'll be printing out the values. Okay, it's the exact same value, but here I have made a new code just to show these are the different values that we use. So let's see like how the signal, speech signal differs from the ppg signal, and how our output differs from both these things. So here this is actually the convolution, sorry, autocorrelation functions output. X represents the input, Y represents the autocorrelation functions output. Here I have a magnification value of 5 and 10, because if I don't put that, like it's difficult for us to see the values. They become so small. So as it has more data, it is having more pages. Let's wait till it uploads. It's uploaded. So let's see how it works in serial plotter. This blue represents the input signal, and every 500 every 200 samples, like 240 samples, like it's giving autocorrelation function. As you can see, like autocorrelation functions works good. So then we'll be finding the autocorrelation. I mean, what is the peak frequency of all those things? So once we know what is the peak, in the sense after every non-zero crossing, the first peak with considering the distance between 0 and the non zero crossing peak. So that is from 0, what is the distance between the first peak value? That's what the peak index 1 represents. And once we know that, we can find the pitch frequency by multiplying into 8000 and dividing by the peak index. That is 8000 samples is there in 1 second, and these many peaks are available in 30 milliseconds. So what is the uh, pitch frequency? This is how we compute, and then we will be uploading it. Oops, I had to upload it properly, I think. Let's upload it and see. It's uploading, and then it should come for all 16 windows. As we are having 16 windows, it should print for all 16 windows. It's still uploading. It's done. So as you can see, it is giving 44. I'll print in a proper way, serial printing. Okay, let me put it this way so that it is easily visible to make sense of what is happening here. So we're giving a space. So what I'm doing here is I'm first printing what is the peak index between two signals, and then I'm printing what is the calculated pitch frequency. So I'm printing pitch average sample so that we can easily make sense of what is happening inside. Which, so now it becomes easy to see like what the code gives and what the output of the code is. The average distance between two samples. It's again uploading. It's almost done. Okay, let's now see how the output looks. So the output comes out to be around like 181, like 186, 190, 205. Here like the signal is not properly, the signal is not sampled properly. So like you can actually see the output almost lies in the range of 180 to 235. So from this we can conclude this is the pitch frequency of uh, yeah, adult woman, because we already have ranges of frequencies. Adult woman ranges from 150 or 160 to 260, and all those samples like if you take for infants it starts with 250 to 650 hertz. So like we have several categories of frequencies, and in this thing the we can actually see it's a frequency of adult as the values rise between 180 to 235, except for these two values. Like that can happen like a small error in the sampling sample data. So we actually found it is to be a pitch frequency of adult female. So this can be extended in real life to see like whether to distinguish the genders with who is talking and who is not talking, and we can actually categorize them. So that's all in this video. Thank you folks. I hope you liked it. If you enjoyed it, like it. Thank you.